there's humans, and they're less predictable than
chess pieces.
Than you have an opponent in chess who's also somewhat unpredictable. But for example, in chess, you always know the opponent's intention. They're trying to beat you, right? Whereas in driving, you don't know, is this guy trying to turn left, or has he just forgotten to turn off his turn signal, or is he drunk, or is he, changing the channel on his radio, or whatever it might be. You got to try and figure out the mental state, the intent of the other drivers to forecast the possible evolutions of their trajectories. And then you got to figure out, okay, which is the trajectory for me that's going to be safest. And those all interact with each other because the other driver is going to react to your trajectory, and so on. So, you've got the classic merging onto the freeway problem where you're kind of racing a vehicle that's already on the freeway, and are you going to pull ahead of them, or are you going to let them go first and pull in behind? And you get this sort of uncertainty about who's going first. So all those kinds of things mean that you need a decision-making architecture that's very different from either a rule-based system or, it seems to me, a kind of an end-to-end neural network system. So just as AlphaGo is pretty good when it doesn't do any look ahead, but it's way, 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 way better when it does, I think the same is going to be true for driving. You can have a driving system that's pretty good when it doesn't do any look ahead, but that's not good enough. And we've already seen multiple deaths caused by poorly designed machine learning algorithms that don't really understand what they're doing.
Yeah, on several levels. I think so on the perception side, there's mistakes being made by those algorithms where the perception is very shallow. On the planning side, the look ahead, like you said. And the thing that we come up against that's really interesting when you try to deploy systems in the real world is you can't think of an artificial intelligence system as a thing that responds to the world always. You have to realize that it's an agent that others will respond to as well. So in order to drive successfully, you can't just try to do obstacle avoidance.
Right, you can't pretend that you're invisible. Right, you're the invisible car.
Right.
It doesn't work that way.
I mean, but you have to assert, yet others have to be scared of you. There's this tension, there's this game. So if we study a lot of work with pedestrians. If you approach pedestrians as purely an obstacle avoidance, so you're doing look ahead as in modeling the intent, that they're going to take advantage of you. They're not going to respect you at all. There has to be a tension, a fear, some amount of uncertainty. That's how we have create.
Or at least just a kind of a resoluteness.
Right.
Let's
yes,
put it that way.
assertiveness.
You have to display a certain amount of resoluteness. You can't be too tentative.
Yeah.
And so the solutions then become pretty complicated, right? You get into game theoretic analyses, and so we, at Berkeley now we're working a lot on this kind of interaction between machines and humans,
and that's exciting. Yep.
And so my colleague Anka Dragan actually, if you formulate the problem game theoretically and you just let the system figure out the solution, it does interesting, unexpected things. Like sometimes at a stop sign, if no one is going first, right, the car will actually back up a little, right? Just to indicate to the other cars that they should go. And that's something it invented entirely by itself.
That's interesting.
Right? There was, we didn't say this is the language of communication at stop signs. It figured it out.
That's really interesting.